Let's now talk about the most common absorbers, which are those due to hydrogen. We can divide them according to the projected column density, as I mentioned earlier. So Lyman alpha forests are clouds which have unsaturated lines, and they correspond to column densities ranging up to 10 to the 16 per square centimeter or thereabouts. They have very little, if any, metals, and their sizes are bigger than those of galaxies. They're not yet collapsed into galaxies. Next are the Lyman limit systems. Those have column densities ranging from 10 to the 16 through maybe 10 to the 18 or so per square centimeters. They're called so because there is enough absorption going on that you can see the break of the Lyman series at rest frame wavelength of the 912 angstroms. The Lyman alpha lines themselves are already saturated, and so it's the amplitude of the break that's actually interesting quantity here. Going to even higher densities, we see so-called damped Lyman alpha systems. They're completely saturated. They're called damped because what you see is the absorption by so-called damping wings of absorption line. And if you've taken any stellar atmospheres or maybe atomic physics that deals with this, then you know what that means. We believe that these high column density systems are almost certainly parts of disk galaxies of high redshift, or at least their progenitors. The things that we can measure, therefore, are the equivalent widths and the broadening. And there are many codes that can be used for this. Now, this is a well understood and well developed art. And so even highly complex spectrum like the one I show you here can be fitted very well with a collection of model lines that go well through the data points. And this is what the damped Lyman alpha system looks like. It looks like there is this hole in the spectrum with kind of curved wings to it, and the amount of absorption determines how wide that system is going to be. So how many of which there are? It turns out that the probability distribution of column densities is a power law, and it's shown here. And it's a power law with a slope of minus 1.7, which is interestingly close to the slope of the two-point correlation function, and that's not entirely an accident. But it goes from the lowest column densities that we see to the highest ones. So now let's take a look at the evolution of these absorbers. Their co-moving number density per co-moving cubic megaparsec changes in time. It's lower here, and it's much higher at high redshifts, and here's a good illustration of this. There are two quasars, very different redshifts, one low, one high, and they've been plotted in the rest frame wavelength, so you see that for the low redshift one, there are hardly any Lyman alpha clouds to be seen. At high redshift, there is ubiquity of them. And so that's probably because these clouds eventually get absorbed into galaxies. Using simple Friedmann models, you can derive formulae that will correspond to number per unit redshift interval as a function of redshift, as a function of cosmological parameters. And here I'm giving you a formula for models with no cosmological constant, although those can be computed as well. And it turns out that also at high redshifts, the number increases as power law of the stretch factor 1 plus z to the 1.8 power. But this does not apply to all redshifts. And one of the interesting results from Hubble Space Telescope was when we can finally observe quasar spectra outside of Earth's atmosphere so that ultraviolet can be observed. Note that the atmospheric transmission window starts around 3,000 angstroms. Bluer of that, it's all absorbed by the oxygen or ozone. But outside the atmosphere, you don't have that limitation. So we could now look at Lyman alpha forest at lower redshifts than we could do from the ground. Say, from the ground you can do from about redshift 1.6, 1.8 up. And from space you can look at arbitrary low redshifts. And it turned out that there is a substantial change in the slope. There is a change in population. This may or may not have something to do with the peak of the cosmic star formation history that happens at around the same redshift. You may think that clouds have been absorbed into galaxies up until then, and then things kind of slow down, so the column density doesn't change very much. And indeed, as you go to higher redshifts, you get thicker and thicker forest. But then what happens is that lines started overlapping. The trees are lined up so dense that you don't see gaps between the trees. And this is illustrated here as a set of windows in redshift space and lines of sight towards some high redshift quasars. At around redshift of 4, you see a very thick Lyman alpha forest, and then it superficially looks like it's thinning out, but actually it's just overlaps of the lines. And what looks like little emission spikes are just gaps between the lines. As you go to ever higher redshifts, it all fills up. And so the intergalactic medium is effectively opaque to the Lyman alpha line. This leads into the so-called reionization that we will talk about in more detail. It is quantified by so-called Gunn-Peterson effect, named after two astronomers who came up with it. And they noticed that if you increase the net column density of neutral hydrogen, at some point it is so saturated that you're just going to completely lose all the flux blueward of the center of Lyman alpha line. It doesn't take a lot. It takes maybe 1 part in 10,000 of the neutral hydrogen in the IgM at that redshift to do this. So recall the history of the universe in some sense is that there is first ionized plasma, it recombines, and this is when the cosmic microwave background is released, at the age of a little shy of 400,000 years. Then there are no sources of light in the universe, and the universe is filled with neutral hydrogen, still some, and neutral helium, as well as dark matter and so on. And that neutral hydrogen would effectively absorb all photons blueward of 1216 angstroms in its rest frame. Radio waves, of course, can still go through. Then sources of light may start turning on. They reionize the intergalactic medium, and thus they make it transparent again to ultraviolet light, except where there are little clouds of hydrogen. And those are the Lyman alpha forest clouds. So the transition from purely opaque, more or less continuous, not very ionized intergalactic medium at very high redshifts to the one that's ionized by stars and quasars is called the reionization era. And until recently, this was one of the major goals of cosmology, to find where it happens. And now we know. The first examples of this were seen circa 2000, 2001 with high redshift quasars discovered by Sloan Digital Sky Survey. And now there is a number of those, several tens, and around redshift of 6, this effect starts to come in. You see sudden drop, essentially complete absorption blueward of Lyman alpha line until you get to sufficiently low redshifts, so then things can start coming out again, and then you run into the limit. This is the end of the reionization era. The beginning starts maybe redshift 20 or 30. That's still subject of some research, but we've seen this signature at least. And we'll talk more about this in the next chapter when we talk about galaxy formation and reionization. So here is a plot of the transmitted flux at Lyman alpha wavelength as a function of redshift from a large number of different quasars. And as you can see, as you go to ever higher redshifts, more and more is absorbed, less and less gets through, and then there is essentially a waterfall, steep cut at around redshift of 6, which is essentially the effect that I just described to you. Next, we will talk about connection between galaxies and intergalactic absorbers.